Hello and welcome to a brief video lecture where I'm going to introduce Kepler's laws. This is the second video lecture accompanying lecture 29. This lecture will cover section 13.5, whereas the first video lecture for lecture 29 covers section 13.4. These are obviously both from chapter 13, covering universal gravitation, and this is for Young 14th edition. Okay, so we're not going to do any examples in this lecture. I'm simply going to introduce the ideas. I don't have any examples illustrating numerical approaches to Kepler's laws because you are not accountable for that information, but instead just need to be able to identify what the three laws are in a conceptual sense. Okay, so let's get to it. So, a little bit of context here. Kepler's three laws are just that. They're laws, and there's three of them. Being laws, there are observations that describe the physical world and have never been disproven. This is distinct from a theory, which is based on a large body of information and hypotheses developed from that information. So, laws are simple and not disproven, okay? They are inherently empirical and observation-based. This is very similar to Newton's laws of motion, okay? Furthermore, interestingly, in a historical context, Kepler's laws predate Newton's laws. They predate much of the classical physics that we have learned up to this point, like conservation of energy and conservation of momentum, especially conservation of angular momentum. And so, in many ways, they have been replaced by these laws that have come later. The historical background is that Kepler was more of a contemporary of Galileo, which would have been a generation before Newton. Okay? So, I'll mention that when we talk about Kepler's second law, because really it's something we've seen before by a different name. But hey, Kepler came first. Okay. So let's get to the laws. So all of Kepler's laws are about orbits. They're based on his observations of observing the night sky with the naked eye. He wasn't using a telescope, unlike Galileo. And that first law says that all satellites have orbits that are elliptical. Okay? So the moon takes an elliptical orbit around Earth. Earth takes an elliptical orbit around the sun. Of course, Earth being a satellite of the sun, the moon being a satellite of Earth, both natural satellites. Okay, so that's Kepler's first law. Now, what's an ellipse? Well, a circle is an ellipse with eccentricity of 0. Okay, so turns out that a lot of orbits, such as the moon orbiting Earth, are pretty close to circular. They're not perfectly circular, and that means that they would have an eccentricity that is very close to 0. Okay, as opposed to a very large eccentricity. What does that mean if we look at a picture of an ellipse like the diagram shown here to the left? Well, for a non-circular ellipse, the distance between the two foci is 2EA. Okay? So E is that eccentricity value, and A is called the semi-major axis. Okay? So, right, where A is the semi-major axis. Now, let's look at the picture. Okay? So in this picture, there's a couple of terminology here, perihelion and aphelion. I'll mention those terms in passing. Perihelion is the term of any satellite of the sun when it is closest to the sun. Aphelion is the term when that satellite of the sun is furthest from the sun. So for example, Earth has a perihelion and aphelion. They're about 5 million miles different from each other, but considering that we're about 150 million miles from the sun, it doesn't actually make a very big difference on our seasons or anything. Okay? Now, further, of interest, we can see that the semi-major axis is this value A. That semi-major axis is measured from the midpoint of the ellipse. The midpoint of the ellipse is defined where the minor axis, that's the axis that passes through the thinner part of the ellipse, crosses the major axis, the axis that passes through the thicker or longer part of the ellipse. All right? So in this case, the y-axis is the major axis and the x-axis is the minor axis. So that's why we call it the semi-minor axis, at least why we call A the semi-minor axis, because it's exactly half, semi, of the major axis, okay? And that, that terminology means that the semi-major axis plays a role very similar to the radius of a circle. The semi-minor axis, or the minor axis for that matter, don't really come up in any of Kepler's laws or for anything that we'll talk about in ellipses in this class. Okay, so that's the synopsis of the key characteristics of an ellipse. Any ellipse is entirely defined by its two foci and the gravitational body is located at one of those two foci. Okay? So that's always the case. So in this case, we see that the sun is at one of the foci. Okay? Is at one focus of the ellipse. Now, when the eccentricity goes to 0, of course, what happens is the two foci, S and S prime, overlap and become one point, the center of the circle. Okay? All right, so there's our brief introduction to what an ellipse is, and then information that all satellites are elliptical. And again, all this information coming from Kepler, this is really not so long after Copernicus came up with the idea that not everything follows around the Earth, right? That the Earth is not the center of the universe. So that gives, I guess, some further context here, right? We're talking in terms of generations. We're about a generation after Copernicus, a generation before Newton, in terms of these ideas that were taking hold in Europe, okay? And this would all have been in the 16th century. Newton would have been in the 17th century. Okay, so moving on to Kepler's second law. Okay, so Kepler's second law is all about these shaded regions in pink here, right? A kind of short, squat shaded region and an elongated, thinner shaded region, and how they relate to each other. Because Kepler's second law states that the area, that would be either of these pink areas here, swept out in the orbit of a satellite is equal over equal times. So that means that if we had a time that we call T0 right there, and T1, the difference between T0 and T1, so our delta T being T1 minus T0, that elapsed time to go from this point to this point near the perihelion would be exactly the same amount of time to go from this T0 to this T1 near the aphelion. Well, that's telling us that these two shaded areas are equal to each other, right? Now, I just kind of drew them to make them look like they could be equal to each other. Perhaps they're not exactly drawn, right? But that's the idea, that equal areas are swept out in equal time, right? Now, in other words, that tells us that the satellite is moving slower or faster when it's near the aphelion. Well, slower, of course, right? Because the distance going from T0 to T1 isn't very great, right? The arc length right there is not very great, whereas the arc length near the perihelion, when the planet is closer to the sun, is much greater. So that means that planets move fastest when they're at their perihelion, when they're closest to the sun. The moon moves fastest when it is closest to Earth, okay? Even if that value is subtle because the orbit is nearly circular. For orbits that are dramatically elliptical, like Uranus or even Neptune more dramatically, objects in the Kuiper belt, comets, these dramatic, very elongated ellipses with very high eccentricity, well, they're going to be moving much, much faster near their perihelion than near the aphelion. Now, it turns out that Kepler's second law is consistent with conservation of energy. We could get the exact same result, right? But conservation of energy came later. Kepler's second law came first. So in a sense, conservation of energy is beholden to Kepler's second law, although it's a more general statement that applies to not just orbits, okay? But definitely we can see kind of the groundwork of where these ideas may have come from. All right, so that's it for Kepler's second law. All right, this is the statement, but you can think of it as functionally just being conservation of energy. All right, so furthermore, Kepler's third law. Now, Kepler's third law states that the square of the period of a satellite is directly proportional to the cube of the semi-major axis of the satellite. Now, I went out of my way to show that this is the case just based off of a free body diagram and the universal law of gravitation. Okay, so Kepler's third law is absolutely supported by Newton's law of universal gravitation. In fact, that was a big part of the motivation of getting that law published and out there, and that was a big discussion within the scientific community in Newton's era. Okay, now what does this look like? Well, this would be stated like this, that t squared is proportional, that's a proportionality symbol, to a cubed, a representing the semi-major axis. Okay, again, observation. Kepler didn't know exactly why it was happening, but he knew it was true, right? And then once it was true, it allowed for a lot of calculations to be made, right? Because once we knew the period of Earth and we knew the semi-major axis of Earth, then we could then find out the semi-major axis of other planets based on their periods, okay? And so on. All right, and then we can say that t squared is equal to r squared if we take r squared as being approximately equal to, r cubed approximately equal to a cubed. In other words, the semi-major axis approximately equal to r for Earth, because Earth is pretty circular in its orbit. Okay? And we can actually write it as an equal sign here with t squared equals r cubed as long as we use the correct units. We have to use t in Earth years and r in astronomical units. Because essentially what we're doing there is we're setting up a different coordinate system, or not coordinate system, a different dimensional analysis system, where we're not using meters and seconds, but instead using Earth years and AU. AU is just the distance of Earth from the sun, its radius of orbit, again assuming that it's circular. And when we do that, then all of the planets follow this exact same relationship. All right. So then basically, if we stick in Earth years and AU, then we could find, if we know R of, say, Jupiter, then we can find T of Jupiter in Earth years. Likewise, or similarly, if we know T in Earth years of Neptune, then we can find R of Neptune in AU, and so on, right? So those units then will allow us to write this as an equation, okay? But if we want to use meters and seconds, we're stuck with proportionality. Now, Newton's universal law of gravitation and the universal constant g allows us to go back to our SI units, and we come up with this key formula. So this is our only key formula, and it's really kind of an extension of the third law. And we can call this formula Newton's synthesis of Kepler's third law, right? So it's taking Kepler's third law and putting it in base units. And here then we have an equation again, not just proportionality, but this is our fitting constant, 4 pi squared over gm. And we know exactly where that comes from the free body diagram. Okay, here I have it as r cubed. Let's just make sure we label everything. T is the orbital period. Excuse me. All right. G is the gravitational constant, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. M is the mass of the center of orbit, so that would be the mass of the sun if we're talking about Earth orbiting the sun, or the mass of the Earth if we're talking about the moon orbiting Earth. Now there's further correction here because that doesn't work perfectly. Just a quick kind of side note if you're interested in this sort of thing. There's something called the reduced mass, which accounts for the fact that the center of mass is not actually at the center of the sun in like the Earth-Sun system. And so when you then have that reduced mass, that actually makes it much more accurate. But sometimes it doesn't matter. I guess I say much more because it's an improvement, and it really completely accounts for that shifted center of mass. But sometimes the shifted center of mass is so trivial in its effect on measuring the period t or the semi-major axis r. All right, and then here I have the radius of the semi-major axis of the orbit, and then here I'm calling it r. We could just as easily call it a, depending on the problem. Okay, so those are Kepler's third laws. A quick summary of what they are so you can identify them for yourself. All right, so thank you so much for watching this video, and please check out the video accompanying Lecture 30, which will be the last video of the semester. Very exciting. All right, so thank you again for watching.